So the solution for the dilemma we had before here, this problem of underfitting, that okay, we have training data, but if we evaluate the classifier on the same data set that we used for training, that we may have a highly overfitting, highly over-optimistic evaluation. So the solution is you probably know, the so-called train and test method. So overfitting is avoided, or at least its tendency is decreased, by just partitioning the labeled data into two parts. We will later see that we even use 3 parts, but so far train and test says use 2 parts, one for training, one for testing. So one partition is used to train the classifier. It has so the class labels are used for building the classification model, and for the second partition, which is the test set, that is only used for testing the classifier. So it's not used for training, it's just used for testing. So the class labels are used for evaluating the classification model. Yeah? And in that case, in the latter case here, the original class labels are of course ignored first. Then we predict new class labels for those in the test set, and then we compare the predicted class labels to the original class labels in the test set, of course. Yeah. And be a little bit aware. Train and test set is not applicable per se, but very often it's a little bit harder to be applicable or to be applied if the training set or the set of labeled objects is very small. Yeah? But in general, it's a very good idea always a good idea to use train and test. And there are different ways to do that, different strategies. So the most prominent thing is probably m-fold cross-validation. So in that case, you decompose not only in 2 sets, but into m subsets, so-called folds. Yeah, that's why it's called m-fold. Yeah, m folds, m subsets should be stratified, meaning that the relative frequency of the class labels in the overall data should be reflected in the folds. Yeah? So if we have, for example, if we have a 50-50 two-class problem with 50-50, 50% class A, 50% class B in the labeled set, then all the folds should also have a 50-50 distribution between A and B. Yeah? And the folds should have approximately equal size. Then we iteratively use m-1 partitions as the training set and the remaining single partition as the test set. And we do that in a round-robin way, so that each of the partitions are at least once used for training and are at least once used for testing, especially. Yeah? So we do that m times, obviously, yeah? And combine the m classification accuracy we get to an overall classification accuracy. And as I said before, the most popular train and test variant. There's a special case, especially for smaller data sets, which is a non-stratified cross-validation, the so-called leave one out, or also known as jackknife strategy. Leave one out, as the name suggests, we take just singleton sets for the test set. So we have, so to say, for each object one fold, meaning that we train on m-1 objects, not folds in that case, but objects. Folds and objects are the same in that case. So we train on m-1 objects, and one object is left out for testing, so that each object is at least again present in the test object at least once. Yeah. So leave one out can be done if O is a little bit smaller, so that the folds here, the m folds are too small, or would be too small. Yeah, and another strategy is the so-called bootstrapping, also for smaller sets, not that bad. So in that case, we build a training set by simply drawing, if we have m observations, then we draw m observations from this set, but now with replacement, meaning that there may be some duplicates that we draw, and statistically, if we think everything is has an equal probability, then we get 63% of all the observations in the training set. Yeah. So some multiple times, and some of the original training set will not be drawn at all, and that will be 37%. Yeah. So we get only approximately 2/3 of all the observations into the training set in that case. Yeah. And the test set will be the entire set in that case. Yeah, bootstrapping usually yields an overestimating accuracy estimation, cross-validation usually conservative, but that is just this usual. Yeah, so doesn't mean it's always the case. So yeah, you can try different things here, of course. Yeah, but if you have enough training samples, then just do a 10-fold cross-validation. Yeah, M-fold cross-validation with 10 folds. And also maybe 10 times, so that is basically the gold standard. If you have enough training samples or label samples, then do 10-fold cross-validation, and not only one time, but do that 10 times, so that you get a real good mix of the different folds. Yeah, so that is key actually, that you apply a lot of randomness to your train and test splitting. That is the most important thing in practice actually. Yeah, evaluation measures, just very shortly. Of course, we want to quantify how good a classification model can predict the correct class. Yeah, so popular measures are, of course, accuracy, error. Look at two different things here. So accuracy and error are, of course, somehow orthogonal. Yeah, accuracy is 1 minus error, and the other way around, of course. Resubstitution error is the error on the training set. True classification error is the error on the test set. The smaller the difference between these values, the better the model generalizes actually. Yeah, so typically you will assume that the error on the training set is a little lower than the error on the test set, because the training set is that what you used for training, and the test set has not been used for training. So the objects in the test set haven't been seen during the training, so you expect the true classification error a little bit higher than the resubstitution error. Yeah, and if but still the difference should be small. If the error on the training set is very, very small, but the true classification error is high, then something is wrong, and typically that means you have a kind of overfitting problem in that case. Yeah. So other things you can look at are confusion matrices, precision recall, F measure, and stuff like that. ROC-AUC curves are also quite interesting. Yeah, the choice typically depends on the application. So sometimes you want to optimize recall, sometimes you want to optimize precision. All these things optimize different things like false positives, true positives, false negatives, true negatives, and stuff like that. Depending on the application, you want you have to choose which one you want to optimize actually.